Hey guys, we're going to go through the 9.5 Handout 1 solutions right now, and there are a few interesting things here that I'm going to point out. So first, we have a siren on a car, must be a police car. I don't think ambulances would be described as cars usually. And our vehicle is moving at 28 meters per second. While it's moving, it is emitting a sound of 1,250 hertz. This car is moving toward a stationary observer, who we will call observer X, and away from an observer Y. So we need to calculate the frequency and wavelength of sound observed by both observers. And the speed of sound in still air is generally about 340 meters per second, although that can vary with temperature quite a lot. So they give it to us here. For other problems, if it's not given, you should just assume that it's 340 meters per second. That would be fine. Okay, based on this information, we need to identify some variables. So first, the velocity of our object is u sub s, and it is 28 meters per second. The velocity in air has been given, 340 meters per second. The frequency is 1,250 hertz. Okay, so we need to decide which equations we should use. So we have a moving source, which means that when you go to your data booklet, you will use the moving source equation. And I've shown both of those here, okay? Now, the question then becomes, how do we decide which one to use? Well, at X, the objects are coming closer together. And when that's happening, we're going to have a higher frequency, okay? So we use this minus sign here because that will produce a smaller value in the denominator, and that will then give us a higher shifted frequency. And that's what we need, okay? So remember, the frequency, the shifted frequency, will be inversely proportionate to whatever is in that denominator. Okay, so we want a higher frequency as our objects come closer together, and we then plug in our values, and we get a higher frequency. There it is, 1,360 hertz. Okay, so that sounds pretty good. So at point Y, the objects are moving farther apart. So that means we're going to have a smaller frequency at Y, and we need our denominator to become larger in order to produce a smaller frequency. Okay, so we plug in our values and we get 1,150 hertz, which is indeed smaller. So that's what we want. Now we need to calculate the wavelength as demanded by the problem. So this is very straightforward. I don't think I need to explain it in detail. Do note that the wavelength at X will appear to be smaller than the wavelength at Y, and that is what we would expect for larger and smaller frequency, respectively. Okay, 9.19 is fairly straightforward, but there are a few things that we need to point out. Note that I've set up the train with an angle here, and the book doesn't really get into this, but I think it's interesting enough that I wanted to cover it, so we will take a look. So we have a train coming on, and you guys should be familiar with the sound of a train coming toward you. And you will note that its frequency is higher as it's approaching, and it's lower as it's going away. The interesting thing here is that this angle is very small most of the time that the vehicle or train is approaching you, okay? It's only not very small for a very, very short window of time. Okay, so as long as we assume that that angle is very small, we can just plug in our velocities and it's pretty straightforward. Okay, and when we do that, we're going to find that as the train is approaching, its frequency is shifted. We have a higher frequency, 512 hertz, as we would expect. Okay, so here's the interesting thing. When the object is going by you, the angle will become large enough that it's going to affect the frequency significantly. And so here, this kind of shows you how the frequency is going to vary as that angle changes. So when the train is directly next to you and the angle is equal to 90 degrees, cosine of theta is going to equal 0, and you will hear the actual frequency of the train when it's right next to you, as you would expect. Okay, when the object is moving away, again, we assume that the angle is negligible. In other words, it's not going to make a big enough difference to consider in our calculations. Here, we need our frequency to become larger. So again, our denominator needs a plus sign in order to make the frequency, the shifted frequency, larger. So we plug in our values and we get 489 hertz. So there's our range, 512 to 489 hertz. Okay, so next page. This one you guys have not seen because evidently the PDF got chopped off, which is really annoying. Word has been doing that occasionally. Images fail to load for reasons that are not entirely clear to me. But it's okay because this problem, it deserves our attention. So let me lecture through it and then you should try some of your own. So we have a sound wave of frequency, 15,000 hertz, emitted toward an approaching car. And in case you're wondering, guys, this is how radar guns work, or laser speed guns, okay? So the wave reflects from the car and then is received back at the emitter at a frequency of 16,100 hertz. So we have a shifted frequency and it's a higher frequency, which makes sense, again, because our car is approaching. So we need to calculate the velocity of the car. And this is going to require 2 steps. So initially, the car is approaching the source. Okay, so we select the correct equation for that. And what we have here is the equation for a moving observer. Okay. After reflection, however, the wave behaves as if it's emitted by the vehicle, okay? And this is where things get interesting. Okay, so I have designated our now twice shifted frequency as F double prime. Okay, so our shifted frequency, our initially shifted frequency, remember, is given by F prime. Okay, so, and we have the equations for both now, and we just need to do a little bit of substitution here. And there it is. So we have F double prime is equal to F prime, which is F sub 0 times the quantity velocity plus the velocity in air plus the velocity of the vehicle divided by velocity in air, et cetera, et cetera. I don't want to go through this whole thing. But as you can see, we will get a final equation that looks like this. And evidently, those of you who have taken your SATs may recognize this equation. Okay, we can then solve our equation for the velocity of our vehicle. And this does involve some kind of annoying algebraic distribution and factoring and so forth. But once we've done all that, we will find that the velocity of our vehicle is equal to the velocity of sound in air times f double prime minus our initial frequency divided by f double prime plus our initial frequency. Okay, and when we plug those in, we're going to find that this gives us quite a small value, and that is generally what we would expect for sound in air. Okay, so your objects moving through air are not usually going to be a significant percentage of the speed of sound. So if you got a really big number here, you'd want to check your math or make sure that it's something that should be moving at a very high velocity. Okay, so here I do a sanity check, and I convert meters per second to kilometers per hour, and I get 43.2 kilometers per hour, which is a reasonable speed for a car. That's not crazy. Okay, guys, that does it. Yeah, as you can see, there's a noticeable bit of math here, algebra. It may be worth your time just to remember this equation. This would work for examples where you have a moving object and you're trying to calculate its velocity. A common application here would be a speed gun, a radar gun. Okay, have a great day, guys. I will talk to you later.